Minutes behind the schedule. So let's start. Our next speaker, after hearing number theory in Canada and Argentina, we move back up to United States, and we will hear Alvaro Lozano Robledo from the University of Connecticut with a talk towards the classification of adelic Galois representations attached to elliptic curves over Q. So go ahead.
Thank you. Thank you so much for the introduction. Thank you so much for the organizers to put this together and for inviting me to speak here. So what I would like to talk about is some progress towards classification of adelic Galois representations. I'm going to explain what those are. The key word here is towards. We're still far from that, but we are trying to make some progress and trying to understand how these work and hopefully have some understanding of what a classification would look like, or at least some conjectural list of possible representations that can appear coming from elliptic curves. So the subject here is the arithmetic of elliptic curves, and to an elliptic curve what we're going to attach is what we call an adelic Galois representation. I'll explain how to build this, but it's a representation of the absolute Galois group of Q that maps to GL2 over the profinite completion of the integers. So that is the inverse limit of all copies of Z mod and Z, what we call the profinite completion of the integers. So that is some very large representation, and we're interested in it because it captures the arithmetic of the points on the elliptic curve. So here in this example, for example, I have an elliptic curve in blue. So here is my elliptic curve, and I have a point of order 5, this point P, and Galois. So if this point is not defined over Q, is defined over some algebraic extension of Q. And when you act with automorphisms of the algebraic closure of Q, it sends to other points of order 5. That's so because the morphism, that is addition, commutes with the action of Galois, because the morphisms are themselves of addition are defined over Q. So in this example, for example, it will send P to 2P, and then once you know that, you actually know where everything goes. 2P would go to 4P, and 4P would go to 3P, and 3P would go back to P. What that gives you is one tiny piece of this adelic Galois representation for this elliptic curve. It gives you a character that gives you, each automorphism will send the point to some multiple of itself, and that gives you a character to Z mod 5 cross. That character, which is the action on one torsion point of order 5, is a piece of what we call row E5, which would give you the entire action of Galois on just the 5 torsion. And now putting all together for any n torsion subgroup, as you put these representations together with some sort of inverse limit, then you build what we call the adelic Galois representation. So here we have the representation that you would get from letting Galois act on point of order n. And if you build what we call the adelic Tate module, so we have n torsion, and we do the inverse limit of the n torsion. Each n torsion subgroup of an elliptic curve as an abstract abelian group is 2 copies of Z mod and Z. So when you do the inverse limit of those groups, what you get is 2 copies of Z hat, and then the automorphisms of the Tate module of this adelic Tate module, the automorphisms will be, once you choose a basis, it will be isomorphic to GL2 of Z hat. So for every automorphism of Q bar, we get some automorphism of the Tate module, so we get an element of GL2 Z hat, and then we get what we call the adelic Galois representation attached to E. And the question is, what possible images can we find? So if we have an elliptic curve, build a representation, look at the image of this Galois representation and see what subgroup do you get of GL2 Z hat, and because the image depends on what basis you've chosen, that says that the images are well-defined only up to conjugation. So you want up to conjugation subgroups of GL2Z hat that can appear as images of these Galois representations. This question goes back to Mazur. Mazur on rational points on modular curves has this question essentially already appears there, what he calls program B, which is in this question is sort of phrased the other way around, that given a subgroup H of GL2Z hat, classify what elliptic curves have that image as a have that group as an image of the Galois representation. I want to go sort of the other way around. I want to classify, given all the elliptic curves over a Q, for example, what images do we get? Okay, so what do we know about this problem? Serre, in his famous paper on the open image theorem, he proved that if E does not have complex multiplication, then the image of an adelic representation is open, is a finite index in GL2Z hat. So, so it's some very large subgroup of GL2Z hat. And moreover, over Q, he showed that the index is always at least 2. So you never get all of GL2Z hat. That's not an allowed image. Over Q, it turns out that over a number of fields, those do happen. And in fact, it follows from the same proof that the index is always even. We'll come back to this in a moment. In the same paper, Serre asks if you can take the adelic representation, if you're afraid of this giant monster, you can reduce everything mod P, and then you get a representation to GL2FP, and then you can try to figure out what images you have there. And Serre asked if you have an elliptic curve with no CM, with no complex multiplication, whether that is always surjective to GL2FP for large enough P, independently of the elliptic curve E. So that's called Serre's uniformity question. And more recently, in terms of indices, Zewina, actually, if you assume a positive answer to this, that this is always surjective for P bigger than 37, Zewina has proved that then if E does not have CM, then except for a finite number of exceptions of some finite number of J invariants, the index is one of these. So there is actually a candidate list of indices that this image can have. This is not the entire list of possible indices. Inside this finite set J, there is some other even larger indices. I'll show you an example in a moment also. Okay, you see that there is all over in this slide, there's if E does not have CM, if E does not have CM, if E does not have CM. That's because the CM case is better understood. The theory of complex multiplication is very rich, and it gives you, the image is more rigid, and we know what happens. So let me just come to explain. I'm not going to read this entire slide, but this is coming from a recent paper of mine where I wrote basically in coordinates exactly what the adelic image is for an elliptic curves over Q, or in fact elliptic curves over any number field that have CM, what the image is. And the short is that there is what we call a Cartan subgroup, and then what we call a normalizer of Cartan in adelically, and such that the image is always contained in this group that you can construct as above. It's always contained in there. And in fact, the index is also controllable. And the index divides the number of units in the ring of integers that you have complex multiplication by. But these rings have their orders in quadratic imaginary fields. So the number of units, it always divides 4 or 6. And in fact, if the J invariant of your curve is not 0, 17, 28, it divides 2. So again, you get that the image is very well understood in complex multiplication cases. Bourdon and Clark, by the way, have a lot of very interesting work on complex multiplication. For example, this part of the theorem they had already shown it before I proved the rest of this theorem. Okay. So something else one can do is the following. So it turns out that Z hat has decomposition as a product over primes of ZPs, of where these are the p-adic integers. So what you can do is, if you have an adelic representation, you can do a further projection and just project to ZP to a p-adic copy and see what the image is there. And there is a lot of progress actually in that in that respect, trying to understand these projections to p-adic images, which correspond to the action of Galois on a p-adic Tate module on points of order a power of p. So it turns out that we know, for example, in 2014, Jeremy Russ and David Zurich Brown proved a complete classification for elliptic curves with no CM. For CM, my work actually completes the classification, what happens with CM. But in any case, with no CM, they classified what can happen with two-adic images. And they show that actually there are 1,208 possible images up to conjugation. And they say more about what those images is, and there's a whole database of images that are available online. More recently, this is like really brand new amazing research. Rouse, Sutherland, and Zurich Brown have a database, a conjectural complete list of all p-adic or L-adic Galois representations. Conjecturally, we still have to assume Serre's uniformity, and there's a couple of other images that they have to assume that there are none of those types, but it's some very concrete images that might or might not happen. Those are also just some like small finite list. So in any case, we know a lot about what happens p-adically. Now, what is the possible image, the largest possible adelic image that one could find for a Galois representation? So Serre, remember, proved that the index is at least 2. So can there be elliptic curves with index 2? If so, we call that a Serre curve. Jones, and then Kujukaru-Grant and Jones have shown that almost all elliptic curves are Serre curves. So if you pick an elliptic curve at random, that elliptic curve will be a Serre curve, that the image is as large as possible, the index is 2. And in fact, but this was proved with Hilbert's irreducibility, and in all their Hilbert irreducibility proofs, it just shows there are infinitely many without actually showing exact examples. And one of my previous students, Harris Daniels, actually constructed the first explicit infinite family of Serre curves. So there is some in his papers, there is explicit curves that you can just look at, and they're very easy to write that are Serre. Okay, so that's the largest. Why is the index even? That comes to the key of what this talk is about, which is what we call Galois entanglements. So it turns out there's 2 possibilities. The discriminant of the elliptic curve is a square as a rational number. If so, remember that the 2 torsion, so if the elliptic curve is given by y squared equals f of x, then the 2 torsion is actually the splitting field, a splitting field of that polynomial f. So if you have a square, the discriminant of the elliptic curve, which is essentially the discriminant of f, is a square, then what you have is that the Galois group is either trivial or cubic cyclic, instead of what should be the largest possibility, which is an S3, the splitting field of a cubic. So in either case, we already have that the mod 2 representation is of index 2 in S3, of index dividing or of even index, and that already forces the two-adic representation to be even, and then the adelic representation would be even as well. The other possibility, which is I think more interesting, is if the discriminant is not a square, then what happens is that class field theory tells you there's going to be an entanglement between 2 different what we call division fields. This is the field of definition of the 2 torsion points and the field of definition of the n torsion points. So in the field of definition of the 2 torsion points, we have always the square root of the discriminant, but by Kronecker-Weber, this is an abelian extension. There's an extension of degree 2, so it has to be contained in a cyclotomic field. And this cyclotomic field, by the existence of something called a Weil pairing, this cyclotomic field has to be contained in the n division field. Okay, so it turns out that then this quadratic extension is both in the 2 division field and the n division field, and that's what we call like a Rho entanglement between these division fields. And whenever the image is smaller, that's what's happening. There is some sort of entanglement, some sort of like intersection between 2 fields that should be disjoint or maximally disjoint for the image to be as large as possible. So let me show you an example. Here's an elliptic curve, and here the discriminant is -43. So that means that the square root of -43 is contained in the 2 division field, but it's also contained in the 43rd cyclotomic field, and therefore it is also in the 43rd division field. So there is an entanglement between these two. In this case, one can show, and in fact, Sayre proves this in his paper, you can show that the two-adic image is surjective. The 43rd adic image is surjective, but it cannot be that the adelic one is surjective because modulo 86, these two have an intersection that makes not possible to have a full image, and the index has to be at least 2. And in fact, one can prove, and Sayre does, that the image is exactly of index 2. Now, pay a lot of attention here. I'm just going to change, just to see how delicate these matters are in the arithmetic of elliptic curves. I'm just going to change this plus to a minus in the definition. So you see now, because this is a minus, now it's changed. The arithmetic changes. Now the discriminant is -11. So again, the 2nd and the 11th division field are entangled. They have an intersection. You can also prove that the 2 division field and the 11 division field, or the 2-adic and the 11-adic images are surjective, but entangled, so that mod 22 is already not surjective. And on top of that, there is something new happening. It turns out that this elliptic curve has a point of order 5 defined over Q. So now we also have to consider what's happening in the 5-adic representation. In the 5-adic representation, the fact that there's a point defined over Q forces the image with respect to a basis, where this is the generator of this subgroup is the first point here. It turns out that that forces the image to be a Borel to some upper triangular matrix like this, and that has already index 24. So the index of the adelic representation from this problem is has a factor of 2, and from this other problem has a factor of 24. So the index is at least 448. But there is more problems for this particular elliptic curve. For this elliptic curve, besides what we've already seen, actually this elliptic curve has an isogeny, a map to another elliptic curve of degree 25. And what that means is that there is a point of order 25 that generates a subgroup that is Galois invariant. So what happens is that modulo 25, the elliptic curve also has, the Galois representation also has an upper triangular image. And now the index in here is 120, and that forces the adelic image to have index at least 240. Whenever there is a presence of an isogeny, the index grows. For example, in this elliptic curve, which is one of those that were in that J from Zewina, this elliptic curve has a 37 isogeny, and then the index of the Galois representation is at least 2736. Okay. So we've seen when is the image largest possible. So also like when is the image, how can the image be the smallest possible? What are the worst possible entanglements? This is some work with Harris Daniels. And here what we've done is try to understand when 2 division fields and the field of definition of the N torsion and the M torsion are, there is a coincidence between the two. So for example, in type of elliptic curve, this elliptic curve, there is a coincidence between the 2 and the 3rd division field. We call that a horizontal coincidence, while in this elliptic curve, the 2nd division field and the 4th division field coincide. So we call that a vertical coincidence. And we've been studying those So we have a couple theorems about what can happen, and it turns out that the vertical ones are not, they don't happen very often. If you have a coincidence that are vertical, then P is 2 and N equals 1, but we have an explicit parameterization of all those. And then we also have something about when roots of unity appear sooner than expected. But let me just, that's a little bit technical. And then sort of for horizontal entanglements, what we can do is check when there are horizontal entanglements between a P power and a Q tower for different primes. And it turns out that the only way this can happen is when P to the N is 2 and Q to the M is 3. If the entanglement is actually an abelian group, then we can actually classify that the only way that can happen is when M is 2 and N is 4 and this happens, or when M is 3 and N is 6 and then this happens. All right. So finally, the latest work we've been doing with this is with Harris Daniels and Jackson Morrow. We are trying to understand what are the types of abelian entanglements. So when you have an entanglement that is abelian, how can that happen? So one entanglement that can happen, that you can imagine happening, is if you have an A division field and a B division field, again, by the existence of the wave pairing, we have the roots of unity are in there. So if for some reason subfield of the 8th roots of unity appeared inside the B division field, then that would give you an entanglement, some subfield that is in both that shouldn't be there in principle. Okay, so that is what we are going to call a Weil entanglement. So we have a number of, we started trying to classify all the possibility of abelian entanglements, and we have what we call the Serre entanglement, which is what I have already told you, an entanglement that has to do with the square root of the discriminant. If there are elliptic curves with complex multiplication, there is always an entanglement that is sort of built in. And we have those Weil entanglements when roots of unity of 1 degree appear in some other field for no good reason. So those happen actually often, or we have large families of such examples. For example, this family of elliptic curves, so for any t and then any d square free integer, we have a family of elliptic curves, and all of those, what happens is that the image, the third image, the mod 3 image, is a diagonal image. And we can actually write down what the field of definition of the 3 torsion for this family is. And as I change D, I get entanglements with other fields. So if Q, this will be contained in some cyclotomic field, and that tells me that the 3rd division field and the N division field are entangled. And I can build those kind of entanglements in several scenarios. And then what we've done is also try to understand what are all the possibilities for abelian PQ entanglements. With Harris, we had already classified what kind of the abelian, what's the maximal abelian extension inside a P division field. We had already an understanding of what those can be. So then what we did is, well, now we have a representation, mod P and mod Q, and I have some image and some image. I have some possibilities of what happens for the P division field, for the Q division field, and then try to see in what ways can there be an entanglement. For example, some interesting example is the following. If you have an elliptic curve, such as this one, where the image of the mod 2 image, the 2 division field is a cyclic cubic, there's another possibility which you have 7 isogeny. So if mod 7, there is a Borel image, then this is an extension. This cuts out an extension of degree 6. So there's a cubic, there's a cyclic cubic inside that extension. And what if that cubic extension coincided with the cubic extension coming from the 2 division field? It turns out that can happen. It actually happens infinitely often. So when that happens, this is not a CM entanglement. This is not a quadratic entanglement because it's a cubic. So it's not a Serre entanglement. And it's not an entanglement field that is inside a division field or inside a cyclotomic tower. So it's not a Weil entanglement. It's some new type of entanglement. And what we've proved is that outside of a finite set of J invariants, there might be a few other examples, but just a finite set of J of isomorphism classes for elliptic crossover Q. Every entanglement between a mod P and a mod Q representation, or between the P division field or Q division field, is one of those three types: a V entanglement, a SER entanglement, or a CM type entanglement. Or we have an entanglement between this 2 and the 7th representation, which is like the ones I've just shown you. Or there is an entanglement between the 3 and the 5th representation, and that's it. Okay, so there are infinitely many, at least these, there are infinitely many of them. And this, there can be infinitely many in some cases. Okay, so that's it. We do have a full classification of when those happen. So we have all the J invariants where those infinite entanglements, or those infinite families of entanglements happen. So we have those completely classified, and we've done other work just try to construct other types of V entanglements. We've also done some work that is a little bit more technical also about what the image of the Galois representation, the CM case is. And then we've also extended some of this work to try to understand Galois entanglements in the abelian variety case, which is the Wild West there, because we have a very little understanding of what torsion is for abelian varieties, the field of definition of torsion and so on. So anyway, that's where we are, and I think I'll stop there. Thank you.
Thank you very much. Great slides.